Good morning, all of you. So, today's class we are going to study about the homomorphic filtering systems. So, the homomorphic filtering systems mainly used for analyzing the speech signal. So, in a homomorphic system, so you can able to see that you have an output signal y of n. So, we know that the y of n equal to x of n, it's convolution of h of n. X of n is an input signal, h of n is a filter response or impulse response, which gives you the output signal y of n. Now this output signal y of n, we are going to apply to a z transform. So this will gives you the y of z expression. Then we are sending the signal to a complex logarithm. So which will produce the output as ln of y of z. Then it is sent to the inverse z transform to obtain y bar of n. So now in the inverse homomorphic system, this x of n, h bar of n is given to the Z transform. Then it is applied to a complex exponential sequence and again applied the inverse Z transform to obtain the x of n and h of n back. So this is what is happening here, like a synthesis of a signal. So that is from the output signal you are going to derive the input signal x of n and h of n. Suppose if you want to study the characteristics of the speech signal, if you have the speech signal output, from that we can able to analyze and synthesize the speech signal. Then we have a concept called spectrum. So in the spectral analysis, you have different filters like short pass lifter and long pass lifter. That means filter, when you reverse the FIL, the first three letters, it becomes lifter. So we have a short pass lifter and long pass lifter. So it is given by the formula. In the case of short pass lifter, it is W bar of LP of n equal to 1 for modulus of n less than or equal to n1, 0 otherwise. And in the case of long pass lifter, W bar of HP of n equal to 0 for modulus of n less than or equal to n1 and 1 for modulus of n greater than n1. So in this case, we are applying this short pass lifter here to this particular substral, and here you are giving the y bar of n as an output. So this will give you the h bar of n as an output. And in this case of long pass lifter, if you give y bar of n as an input and which is applied to this long pass lifter, it gives you the x bar of n as an output here. So now in this homomorphic signal, particularly in the speech signal analysis, we can correlate each and every expressions here. So the x of n, it is like an air pressure. The source one, the x of n is an air pressure which is offered on the vocal tract. And h of n is nothing but it's the vibrations which alter this air pressure, and y of n is a speech signal. So if you see the x of n, the input signal is used to estimate the pitch. H of n is used to determine the vocal tract characteristics here. So if you want to analyze the speech signal, we are using this homomorphic filter. In that we will be using Q frequency range. The frequency, when you reverse that first four letters, it will be Q frequency range. So you will be using a short pass lifter and a long pass lifter also. That functions it's given by the mathematical expressions here. So now in the homomorphic filtering, so you are applying a y of n which is equivalent to it's a combination of an input signal convoluted with the impulse response. So this is sent to a discrete Fourier transform. So which converts the time domain signal into a frequency domain signal. Then it is sent to an algorithm. Finally, again the inverse discrete Fourier transform is applied to convert the frequency domain signal into a time domain itself, signal itself. So you'll be getting y bar of n. When this y bar of n it is passed to a short pass lifter, this will give you the output as impulse function h bar of n. When the same y bar of n is given to a long pass lifter, it gives you the output by x bar of n. Then this x bar of n is into a DFT, then exponential and IDFT which gives you the x of n. And this h bar of n is into the again DFT, exponential and IDFT which gives you the h of n. So that means from the output of the speech signal y of n, we can able to determine the input signal characteristics and the filter characteristics like x of n and h of n. So this can be achieved by using this homomorphic filtering. Then when you see the application of a substrum, so we have the example called visually evoked potential. So you know that in case of visually evoked potential, you'll be giving the stimulus and getting the response of it. How your eye responds for getting the stimulus. So how your brain responds during the time. So that will be recorded as a visually evoked potential. So now to prove that, let us have an x of n consists of a composite signal and s of n is a wavelet. So now when it is expressed in the analog domain, x of t equal to s of t plus a into s of t minus t naught. This then when you can express in terms of discrete domain, so it will be x of n equal to s of n plus a into S n of n minus n naught. This S of n represents the present response. S of n minus n naught represents the response for the previous first stimulus. So then this x of n, it is represented as S of n into P of n. This P of n is nothing but the filter. So here it is given by del of n plus a into del of n minus n naught. That is the impulse function plus a constant multiplied by a delayed version of the impulse function. This you give the filter response like P of n. Now in this expression you have to take the z transform. So you will be getting x of z equal to x of s of z into p of z, and this p of z equal to 1 plus a into z power minus n naught when you apply the z transform for it. Then after that you have to apply the inverse z transform for this natural logarithm of s of z plus inverse z transform for natural logarithm of p of z. So this will gives you the output, that is inverse the transform of a natural logarithm of the s of z will remain as such. When you apply the inverse the transform for p of z, which is nothing but 1 plus a into z power minus n naught, you have to expand this logarithmic series. So when you expand this logarithmic series, it will be a into z power minus n naught minus a into z power minus n naught by 2 the whole square plus a into z power minus n naught by 3 the whole cube. So the next expression is, in this case of is x bar of n, this inverse the transform of ln of s of z is s bar of n plus a into del of n minus n naught plus a minus a squared by 2 del of n minus 2 n naught, like that. So next these other eliminating, we will be eliminating the frequencies like f naught, 2 f naught, 3 f naught, like that, when it is applied to a com filter. So you will be getting the x bar of n equal to s bar of n, which is nothing but the input signal. It is equal to the actual signal without any noise. Thank you.